that effect, I'm going to have to multiply by 2 to ensure that the value is the same. So this is 2 times the integral of a half times 1 over root x kind of thing. Cool? All right. So what will happen is that these will cancel, but we're not canceling them out because we want it to remain in a specific format so that we can actually integrate. Ready? Then I'm going to have e to the root of x dx. Now, if you realize this here is the differential, so this here is f prime of x, and this here is f of x. So whenever we have f prime of x multiplying e to the f of x, then it just gives me e to the f of x, which is e to the root x in this case here, plus c. But you can't leave off your 2, so you have to write it as 2e root x plus c. All right? So those are 3 of the 4 results that I'd like you to pay attention to, right? But I figure more or less that math is draining, it drains me too. So I'm just going to give you a quick 2 to 3 minute break, then we'll look at the 4th result. All right, so again, a quick 2 to 3 minute break, then we'll look at the others. If you have any questions about what we've done so far, you can indicate them via the chat room, and within the break, I can probably address it. All right, so 2 minute break. So the final results, the result that I left for last is what we call a integration chain rule, right? But it's you have to be very careful with it because you will think it will work, but it won't always work. So it's what we call integration chain rule in a sense. So integration chain rule. So what we do here is the steps are to 1, integrate the outside function, integrate the outside function, right? And then after integrating the outside function, you are going to divide, not multiply. So remember, in your differential chain rule, you normally multiply. We're doing the opposite. So we're going to divide by the differential of the inside function. So once you can remember this chain rule here, then it simplifies a lot of stuff for you. So divide by the differential of the inside function. All right. So what we'll do here is we're going to establish a few examples that will show you how this one actually works. So for example here, I'm going to start with something easy. What is the integral of 4 times 4x plus 3 all raised to the 4th dx? So you realize that this is a composite function, and chain rule is normally used for composite functions, right? So what I'm going to do, the inside function is 4x plus 3. The outside function is everything raised to the fourth whole. First step says that you're supposed to integrate the outside function. So when I integrate the outside function, it's actually going to give me, when I integrate 4x plus 3 to the fourth, it's going to give me 4x plus 3 to the fifth divided by 5. Now remember that there was a 4 at the start. Don't leave that out. So divided by 5, so I integrate the overall outside function. Then now it says that you're supposed to divide by the differential of the inside. So when you're dividing, all you do is just multiply by 1 over the number. So here, when you differentiate the inside function, which is 4x plus 3, differentiate that to get a 4. What's going to happen now, don't forget your plus c because it's indefinite integral. What's going to happen now, guys, is that the 4's here are going to actually cancel each other. So when you look, this differential reduces to give you 4x plus 3 all raised to the fifth divided by 5 plus c. So that would be your first example. So that's how you work with the chain rule. Now, I'm going to be very, very cautious because there have been days when I'll try the chain rule and it doesn't give me the correct answer. Why? In order to ensure that your answer is correct, you always should differentiate it and see if you get the same thing as that you started with. So there's a rule, remember that integration is the reverse process of differentiation. So if you integrate and get a result and not so sure if it is correct, differentiate it and see if you get by the starting point. If you don't get by the starting point, then your answer definitely wrong. And I'll demonstrate one scenario where this chain rule does not work. All right, I'll just demonstrate it. Ready? But before I demonstrate it, let's look at another example 2 here. Ready? So what if I asked what is the integral of e to the minus 2x dx? So here, you probably wouldn't be able to pick up. And remember I said that substitutions will also work for all of these. Every single result that I just gave you, a substitution could reduce it. But if you know the result, then you basically save your time in the exam. Now, for this one here, the outside function will just be e to the x because that would be the overall big function. But the inside function now will just be the minus 2x portion here, right? So this is the inside function. So when I integrate the outside function, which is just e to the whatever, will give me back the same thing. So e to the minus 2x here, right? So that's integrating the outside function. Then remember, I need to now divide by the differential of the inside function. So when I differentiate minus 2x, it's just going to give me a minus 2. And remember, I'm dividing. So it's just 1 over the number, then plus c. When I simplify this now, it just gives me negative a half e to the minus 2x plus c. Also, let me just say, if you're practicing and you're not so sure about your answers, there's an online site called Symbolab. It's what we use in math if you're not so sure. You can solve anything you want. You can do differentiation, you can do limits, you can do Maclaurin and Taylor series, you can do everything. It's like if you're a math student and don't know what Symbolab is, you're not really a math student. So if you're having problems while studying and you want to double check your answers and you're not so sure, Symbolab. Let me just write it. Symbolab. It will tell you the answer, but it won't show all the steps. You'd have to buy a subscription for all the steps, but you get the answer, so it really no matter. All right, so let's look at one example now. So this example here is now sine of 9x dx. So this is the final example. Now, the outside function is just sine, right? Cool. And the inside function here will be 9x. So this is inside, and this is outside. So the rule says that you are supposed to integrate the outside function. When I integrate sine, I get a minus cosine. So I get minus cosine. Cool. Now you don't change the inside value, just minus cosine of 9x, right? Then I'm going to divide by the differential of the inside. When I differentiate 9x, I get 9, right? So I'm going to have a plus c now. Simplifying, this is negative 1 over 9 times cosine 9x plus c. Now, I'm going to demonstrate a scenario where this does not work. So, when the when the chain rule here does not work. So what if I asked you to integrate, say, cosine squared x dx? Now remember, this does not work. So I'm just demonstrating why it doesn't work. If we were supposed to use the chain rule, then we could write it as cosine x all squared dx, and then we can use the same thing that we did, right? So integrate the outside function, I'd integrate the square function here. That'll give me cosine of x all cubed over 3. Then I'll divide by the differential of the inside function, which will give me minus sine x plus c. Now, if you were supposed to integrate this, lovely people, you would not get the starting point that you started with. So if you were to differentiate this, if you were to differentiate this result, you would not get cosine squared x. And you don't even have to differentiate it to tell. Because if you're supposed to differentiate this expression, it's a quotient. So you already know that the quotient is going to be sine squared x. And the fact that you have sine squared x in the denominator just tells you right away that you're not going to get a cosine squared x as your final answer. So it's very evident that it wouldn't reduce, right? In fact, if you wanted to integrate this, if you wanted to integrate cosine squared of x dx, you would have to use the identity that cosine of 2x is equal to 2 cosine squared x minus 1, and then transpose 4 cosine squared x, which would give me cosine 2x plus 1 all divided by 2, and then use this and integrate it. But that's more of like a more rigorous kind of answer. I doubt they'd give you something like this to trick you. But all I'm saying, when you use the results, check it. Please check it to see that your answer is actually correct. How do you check if your integral is correct? Differentiate the result and see if you get back the same. All right. Now, we're running out of time because like we literally must end at 5. So what I'm going to do, I'm actually going to do the next part of the topic now, which is substitution. And then I'm going to do integration by parts. There's a really, really easy and short way of doing integration by parts. And once you can get that short way, then you really and truly don't have to pay attention to anything else. It's what we call the tabular method. So some teachers probably give it a long UV, differentiate this, differentiate that, and multiply them, whatever, whatever. But once you know the tabular method, then you're very much on your way, all right? So it's the same answer. But what I'm going to do, I'm going to look at substitution method. Now, remember that every result that we just got from before, every one of these can actually come from the substitution method, right? Let me just make this properly. So in fact, this is equal to the cosine 2x plus 1 over 2 dx. All right. So the substitution method, right? Everything that you just did is derived from the substitution method. But there's some of the cases where you literally can't reduce it. Yes, so you can't reduce it to one of the specific formats. So you have to do an actual substitution. Ready? So, for example, here now, the rule of thumb is that we normally, rule of thumb, we normally, not always, so we normally substitute for the inside function of the composite function. So that's just a rule of thumb that we